So this week's lab, the actual lab, will deal mainly with the blood pressure and blood flow. What factors affect blood pressure, how are they regulated, and how do they kind of interact, and then also blood flow. Blood flow has to be with the flow of blood through those vessels. Okay, so we're going to deal with the pressure that exerted on those vessels and also the flow. And we're going to see we're going to have to regulate these. Especially blood pressure. We don't want blood pressure to go too high. You have these nice little delicate vessels in your brain, and if your blood pressure goes too high, they can actually burst. You also don't want the blood pressure going too low, because the blood pressure is basically the driving force for pushing the blood out to the tissues. So you don't want to have it go too low, because that way you're not going to be able to successfully supply blood to the tissues. Okay, so we're going to deal with that. We're actually going to look at the cardiac cycle. It's not specifically with blood pressure and blood flow, but it is one of the factors in helping to regulate these two factors down here. Okay, so we're going to start with the cardiac cycle, and then we'll move into blood pressure and the blood flow portion. So our cardiac cycle, what is it? It's basically looking at the series of events that take place during one complete beating of the heart. And if you remember, the atriums contract, then the ventricles. But what we're going to look at is the flow of blood, and specifically we're going to be looking a lot at the left ventricle. So left ventricle supplies the blood, or pushes the blood out into the vessels that are going to supply the tissue. Okay, but all the events taking place, remember the flow of blood, we're going from, we're going from the atrium to the ventricles, or right atrium to the right ventricles, up to the pulmonary trunk. Once we've gone to the lungs, we return back to the left atrium. Left atrium pumps into the left ventricle, and then left ventricle out into the body. So we're going to look at these series of events that are taking place during this cardiac cycle, during this beating, each beating of the heart. And we can see this cardiac cycle, if we look at our average resting heart rates, say it's roughly around 75 beats per minute, divide that by 60 seconds in a minute, you can see this cardiac cycle, this full cycle of events for one beating of the heart takes place in less than 1 second. All right, and we need to bring in some terminology on what's taking place in the heart. We'll be looking at what's called systole. We have atrial systole. So systole is when it is in contraction. So atrial systole, when the atriums are in contraction. Ventricular systole, when the ventricles are contracting. And then we have a quiescent period, or what we call diastole, when the atrium ventricles are at rest in relaxation. Okay, but as we move through this cardiac cycle, as the blood moves through, we're going to see there are pressure changes taking place, and the volume of blood is going to be changing because we're moving and pumping the blood through. Okay, remember the chambers, our heart chambers, when they're contracting, they're becoming smaller. And when they become smaller, they create larger pressure. When they're relaxed, there's low pressure. When they contract, there is high pressure in their chambers. And what we're going to see is that's the driving force for pushing the blood. The blood is going to go from an area of high pressure to an area of low pressure. Okay. And then also, as we move through the cardiac cycle, we're going to see there are some heart sounds that take place when the doctor listens to your heart. You hear this lub-dub, lub-dub, lub-dub. Okay, 2 heart sounds, and we're going to be looking at valves. Okay, so we're going to be looking at this flow that's taking place, how the blood's moving, what's preventing it from going backflow, and all these events that are taking place during this one beating of the heart, this one cardiac cycle. So as we start going in through the cardiac cycle and the events taking place and how blood is flowing through this heart and what's taking place to move this blood, we got to do a little anatomy lesson to get us up to date with our heart valves. But one thing to realize, as the cardiac cycle is taking place, the heart's either in diastole or systole, in contraction. And what that's doing is, if you remember, when the heart muscles contract, they are making those chambers smaller and increasing pressure. When the chambers are relaxing, all right, pressure is going down. So we're going to be making the heart contract, and we're going to be changing pressure, and that's going to be the driving force for flowing blood through the heart. Blood is going to flow from an area of high pressure to an area of low pressure. Okay, so that's essentially what we're doing. We're creating that force when we contract it to create high pressure to move it to an area lower pressure. Okay, and what we're going to see, we need to look at our heart valves, because there's going to be times, and let's just walk through the flow of blood through the heart. So when we look at this Wigger's diagram, it'll make a little more sense on what's taking place. But blood returns here to the right atrium. Right atrium pumps blood into the right ventricle. And if you remember, the right ventricle pumps blood up to the pulmonary trunk, out to the pulmonary arteries, and back up to the lungs. We get the oxygen, and now the blood's going to return back here to the heart at the left atrium. Left atrium pumps into the left ventricle, and then the left ventricle is going to pump out into the aorta. Okay, so as the heart's contracting and relaxing, it's going high pressure, low pressure, high pressure, low pressure. And what we're going to see is there are times in where the blood may want to backflow. Okay, if we pump into an area, and now this area is high pressure, but the heart's low pressure, the blood's going to want to flow back into that low pressure region. And that essentially is what our heart valves are for. And we have 4 of them. We have 2 valves are called our atrioventricular valves, our right atrial AV valve and our left AV valve. You might know that as bicuspid for the left and tricuspid, okay, for that, or also the left AV valve, also known as the mitral valve. And what these are going to do is, because remember, we want the blood flowing from atriums to ventricles, ventricles out to the aorta. We don't want it flowing in a backwards direction. And so that is what the heart valves are there for. They're preventing the backflow of blood. Okay, because there's going to be a time when the ventricles are in contraction and the atriums are in relaxation. So if my atrium's in relaxation, pressure is low here and my ventricles are contracting, pressure is high in my ventricles, blood would want to flow back here into the atrium. We don't want that. We want the blood flowing from here into the pulmonary trunk. So that is what the valves are for. Specifically, the right AV valve is to prevent blood flow from the right ventricle when it's contracting into the relaxed right atrium. Okay, what closes these valves is the blood trying to rush back actually shuts those valves shut, snaps those valves shut. Okay, there's no muscles causing the contraction. When the ventricles are contracting, chambers getting smaller, the blood wants to flow back here to the right atrium, but as the blood tries to flow back, boom, the valves get snapped. And what we're going to see is those valves are going to be able to cause heart sounds to take place. Okay, the other set of valves, the semilunars here, and that's the pulmonary semilunar and the aortic semilunar. Okay. When the ventricles contract, they push the blood into those large arteries. When you go to measure your blood pressure, you know your arteries have pressure in them. So ventricles contract, push blood into the arteries. There's pressure in there, and when the ventricles go to relax, there's low pressure in the ventricles. And that blood in those arteries is going to want to flow back into the ventricles. And we don't want that to happen. And so that is what those semilunar valves are there for. When the blood tries to rush back, boom, they snap shut, preventing the blood to backflow into the ventricles and can produce a second sound. Okay, so like I said, when those valves snap shut, they are creating heart sounds. There's turbulence. When they snap shut, it creates turbulence in the blood, and that creates a sound. All right, when our AV valves snap shut, that gives us our first heart sound, the lub sound. And when the semilunars snap shut, that gives us our second heart sound. Okay, the lub dub. So when the doctor listens on their stethoscope, lub dub, lub dub. Okay, that's what he's hearing, is those valves snapping shut. Okay, what happens if, say, the valves don't completely shut? You can get what's called a heart murmur, like a whooshing sound, because some blood is being allowed to backflow a little bit. Okay. And there also could be a stenotic high pitch if the valves are old and crusty, like your professor. They may not open all the way when blood's being pushed through them, and that would give you a screeching sound. What heart murmurs are, there's blood being backflowed. The valves don't completely shut up. So now we're going to go through the events that are taking place in each phase of the cardiac cycle. And you look at the bottom here, you can find the different phases. Phase 1, 2A, 2B, 3. Okay, and these vary in what book you're looking at. If you look at the Silverthorne book that you guys have, this ventricular phase will actually be divided into atrial diastole and ventricular diastole. Okay, but what we're going to do is we're going to walk through here. We're going to look at each of these phases: ventricular filling, okay, atrial contraction, isovolumetric contraction phase, ventricular ejection phase, and isovolumetric relaxation phase. So we're going to look at these phases, but we're going to be looking at what's taking place in what's called the Wigger's diagram up here. See, the Wigger's diagram has lots of information, and we'll look at the different details, but you'll see the ECG that we just went over last week. You can see it shows where the heart sounds are taking place. Okay, if you remember the heart sounds from those previous slides is where the valves are shutting. Okay. This graph here will probably focus mainly on here and this part here, but this portion here shows pressure changes. And specifically, we're looking at the left atrium, left ventricle, and aorta. You can see the red here, left atrium, left atrial pressure. The blue is the left ventricular pressure, and the green is the aortic pressure. Okay, below that, it's looking at what the volume of blood is in that ventricle, in the left ventricle, as you go through these different phases. And then finally, what are the states of the valves during each of these phases? Okay, like I said, we're going to spend most of our time, we'll look at the phases, but we'll look chiefly at the pressure changes taking place and also what's taking place in the valves. Okay. So we're going to start in the first phase with ventricular filling. And so just a reminder, as we look at blood is always going to move from an area of high pressure to an area of low pressure. And so when we look at this ventricular filling phase, okay, you can see what is the pressure. Red is the atrium, blue is the ventricle, and you can see the pressure is low in both of those chambers. And therefore, blood that's returning, remember blood returns from the veins, vein returns the blood to the heart. When that atrium and ventricle are both relaxed, the pressure is low in the heart, and blood is just passively filling into those chambers. And you can see that with this ventricular volume change. In this phase, you see the volume of the blood in the ventricle increases. That blood is just passively filling in because the heart is at rest. It's all relaxed, pressure's low, blood just passively fills in. Okay. AV valves are open because AV valves, the blood's going in the atrium and passively filling into the ventricles. What we'll see is the semilunar valves are closed at this state. We'll see how they get there. Okay. And thing is, you see that, okay, 80% of the blood before the ventricles actually contract to push the blood out, 80% of it comes in during this ventricular filling phase. Okay, you'll see actually in your book it calls it early and late diastole, but diastole meaning the heart is at rest and low pressure. Okay. In the end of phase 1, okay, the heart's been at rest. The first thing to take place is the ventricles, or sorry, the atrium going to systole. The atriums contract. Okay, you can see it here lined up with our ECG. Hopefully you now know P wave, that's the depolarization of the atrium. That's going to cause atrial contraction. And what happens to the pressure in the atrium? Yeah, they're contracting, so they increase. And where is that blood flowing? When the atriums contract, they're pushing blood into the ventricles. And you can see as the atriums pressure rises, so does the ventricular pressure, because blood from the atrium is being pushed and causing more pressure in the ventricles. Okay, you can see atrium's pushing blood in. You can see a slight rise. So the remaining of the blood that's going to be in the ventricles before they start to contract occurs during atrial systole here. Okay. And at the end of this phase, we get what's called EDV, end diastolic volume. What is the volume of blood after the ventricles have been in diastole? So before the ventricles go into systole, that end diastolic volume, that's going to tell you what the volume of blood is before the ventricles contract, and ultimately will push blood out of the ventricles. Okay, the EDV will be the highest of volume. Okay, and so then that moves us after the atrials have gone into contraction, push blood into the ventricles. Now we move into what's called phase 2A, and it's called isovolumetric contraction. Okay, this is the interesting part of the pressure curves here. Okay, because remember, blood is only going to flow to an area of area of low pressure to an area of high pressure. So isovolumetric, you might see it as isovolumetric ventricular contraction, but iso meaning same, and volumetric, same volume. Okay, that means, and you can see it here, that the volume of blood in the ventricles is not changing during this phase, but the ventricles are going into contraction. Right? And look here. Here is ventricular pressure. Ventricular pressure starts to rise, and you can see it's meeting with the atrial pressure as it climbs up. Right here is where the ventricular pressure exceeds that of the atrial pressure. Remember, the atriums when the ventricles are contracting, the atriums are going into relaxation. So the atriums are going to be low pressure, and as the ventricular pressure rises, where would that blood want to go? The blood would want to go back into the atrium. And you can see what prevents that. Remember, our AV valves. And when our AV valves close, that's when we get our first heart sound. So you can see that happening right as the ventricular pressure is climbing higher than the atrial pressure. Okay, but this whole step up here, okay, till we get to meet the green, till we get to meet the aortic pressure, is the isovolumetric contraction. Because where is the ventricles? The ventricles are pushing blood, are going to push blood into the aorta. But all through this phase, the ventricular pressure is lower than the aortic pressure. So blood is not being pushed out of the ventricles. Remember, blood's going from an area of high pressure to area of low pressure. At this point, the pressure in the ventricles is lower than the aorta, so blood's not going to be pushed into the aorta. Okay. And when you ever see we're going to see isovolumetric contraction and isovolumetric relaxation. The volumes aren't changing, then bloods aren't being pushed through any of the valves, because blood's got to be pushed through those valves. So during the isovolumetric contraction and relaxation, you'll see both the AV valves are closed and the semilunar valves are shut, because blood is not moving out of the chamber, out of the ventricle. Okay. As the ventricles continue to contract, the pressure keeps going up, 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 and at a certain point, you can see the pressure goes above the aortic pressure. All right, right here is where we start what's called ventricular ejection phase. And you can see the aortic pressure basically shadows that of the ventricular pressure. Okay, because blood is now being pushed out into the aorta. So when this happens, what valve would be opening? Yeah, the semilunar valves, because blood's going from the ventricles out to the aorta. That means the semilunars have to open for blood to pass through out to the aorta. Okay, as the ventricles continue to contract, eventually they're going to start repolarizing and going into relaxation. All right. Now you can see going to be this new phase here. Let me get through processes here. One last thing to note in the ventricular ejection phase is looking at that is when the blood is pushed out. Alright, so you can see the volume of blood is going down in the ventricles because that blood is being pushed out into the aorta. Okay, and at the end of ventricular systole, there is a what volume of blood is left over is called the systolic volume. Okay, and if you remember, we will be talking about what's called stroke volume. Stroke volume is how much blood is pumped out of the ventricle each time the ventricle contracts. And so the stroke volume could be calculated by taking the EDV minus the ESV to tell you what the difference is, and that difference would be the stroke volume, how much blood is being pushed out of the ventricles. Alright, so we are here, and we're going to start this relaxation of the ventricles, and you can see pressure starting to decrease. Okay, as the aortic pressure, this ventricular pressure starts to decrease, at one point it decreases lower than the aorta. So now as we reach into here, as the ventricular pressure continues to decrease, the pressure is higher in the aorta than it is in the ventricles, and blood's going to want to, from the aorta, is going to want to try to rush back into the ventricles. But what happens? The semilunar valves snap shut. When the semilunar valves snap shut, we get our second heart sound. Okay, so all through this phase, okay, the semilunar snaps shut, and the AVs are still shut because the ventricular pressure is greater than our atrial pressure. And so during this isovolumic relaxation phase, again, no volumes changing, so both valves are shut. Okay, there is no change in volume of blood either. Okay. And then once the ventricles are back and relaxed, that ends one cardiac cycle. This was all one cardiac cycle. We start the cycle all over again. Okay. One other note is you see this bump in pressure in the aorta. That happens due to the closing of the vein, or the closing of the semilunar valves. Okay, the blood's running back, pressure's a little bit lower, there's not as much stretch on the walls, but as soon as you snap those valves shut, initially there's going to be, boom, a bump of pressure on the walls of the aorta, and that's where you get this, boom, this dichrotic notch, this bump in pressure in the aorta. So we now have looked at one full cardiac cycle, how the blood moves through the heart, and we've seen in the left ventricle it pushes the blood out, and when it pushes the blood out, we saw that equals to our stroke volume. And now we'll see one of our stroke volumes is a factor in what we call cardiac output. Okay. And this blood, one of the main functions of pushing the blood out is to create enough pressure. It's one of the factors in creating blood pressure, the pressure that is exerted on the walls of the arteries. This is important because this is basically the driving force for creating pressure to push the blood out to all the tissues throughout the body. Okay, we got to maintain blood pressure within a certain range. We don't want it too high, we don't want it too low. Okay, again, if it goes too high, there's small vessels that can be burst, or if it maintains high for a long period of time, your heart will have to work against that extra pressure, and it can be taxing on your heart. Also, we can't have blood pressure going too low. If you think about it, when we're standing up, where's our head? Our head is above us, so we have to have enough pressure to overcome gravity to get blood up to our brain. Okay, so we got to maintain this blood pressure within this homeostatic range. So what we'll look at here is the factors that affect blood pressure. Okay, 2 of these are chiefly maintained by the nervous system, the autonomic nervous system. That's cardiac output and total peripheral resistance. And then when hormonally gauged is blood volume. Okay, but let's first look at cardiac output. Okay, cardiac output, CO, is equal to stroke volume times heart rate. Okay, stroke volume is how much blood, each time that ventricle contracts, how much blood is pushed into the system. Okay, heart rate is how many times the ventricle is contracting per minute. So basically what cardiac output tells you is what volume of blood, how many liters of blood is pushed out in each minute of the heart beating. Okay, and you can imagine if we're pushing more blood out into the arteries, that's going to exert more stretch on the wall. So with cardiac output, if you increase cardiac output, you would also increase blood pressure. Okay, total peripheral resistance. The main factor drawn in this is the dilation and constriction of the blood vessels. Our blood vessels can be wide and dilated or constricted. All right? Resistance. If there is more dilation, there is less resistance in this large vessel than there is in a constricted vessel. Okay, so again, you have vessels throughout the body. This is looking over all your vessels. And certain regions can be dilated, and certain regions can change constriction. When you exercise, you have large dilation to the muscles that you don't have when you have at rest. Okay, so if you add it all together, that would give you your total peripheral resistance. Okay, so if you have dilation, total peripheral resistance actually goes down. If you have constriction, though, total peripheral or more constriction, you would have total peripheral resistance going up. Just like cardiac output, if total peripheral resistance, there's more resistance, goes up, then also blood pressure goes up. Okay. Blood volume, okay, hormonally controlled, chiefly. And you can imagine if there's more volume of blood in the system, if the amount of vessels hasn't changed, but the volume of blood has, that's going to exert more pressure on the vessels. And so also as blood volume goes up, so does blood pressure. Okay, since this is hormonally controlled, for the most part, this is a slower response. If we have things happening that we need immediate changes in blood pressure, and how can we make changes to overcome this? We can use cardiac output and total peripheral resistance, because our autonomic nervous system is going to be controlling this total peripheral resistance and this cardiac output. So those factors that we talked about are going to help regulate this blood pressure. And as we said, that blood pressure is basically that force that is exerted on the walls of the vessel. You see there's pressure force pushing out on the walls. Okay, if there's more pressure, that means blood pressure is higher. If there's less pressure on those walls, blood pressure is lower. And we have 2 readings for blood pressure that we take. If you were going to go to the doctor, they would be taking your blood pressure, and you would get a reading for what's called systolic pressure and diastolic pressure. And what this is, and values, hopefully you're around 120/80. They're actually looking at even lowering this amount. Blood pressure, lower blood pressure is usually better as long as it's not low enough where you're feeling dizzy and so forth, because then your heart doesn't have to work as much against the pressure. Okay, but 120/80 right now is what we consider the norm. And there's two readings. We got the 120, which is the systolic pressure, and the 80, which is the diastolic pressure. Okay, and what this reading is at systole, meaning when the ventricles are in systole, they are pushing blood out in that ventricular ejection phase. They are pushing blood out into the arteries. If more blood's being pushed in the arteries, you can imagine there is going to be more stretch, more pressure on the arterial walls, and that's why this number is higher, because systolic pressure is when the ventricle is ejecting blood into the arteries. Diastolic pressure is when the ventricles are in diastole. Okay? When the ventricles are in rest, there's no blood being pushed into the arteries. Okay? There's less stretch on the vessel walls, and therefore you get this lower number. Okay? But there's changes in this pressure when you exercise and so forth. Pressure is going to go up, but not too high. So we're always kind of taking those factors we just talked about, the cardiac output, the total peripheral resistance, and blood volumes. These factors are always regulated. If you have, say, cardiac output, your heart rate goes up super sky high, and you don't change anything in this total peripheral resistance, your blood pressure is also going to go sky high. And you can see that, okay, the equation here, arterial blood pressure, okay, is governed by cardiac output times total peripheral resistance. So what I was saying is, if your cardiac rate, your heart rate goes up to say 180, that's going to bring your cardiac output extremely high. If you didn't change this value at all, that would also bring arterial blood pressure high. So what must happen with total peripheral resistance if cardiac output goes extremely high? What do we have to do with total peripheral resistance? Yeah, we have to bring it down. If we dilate more vessels, we bring total peripheral resistance down, and that helps counteract this climb in cardiac output. Okay, the vice versa of that. In total peripheral resistance, when you start to exercise, okay, your vessels to your muscles dilate. Dilation causes total peripheral resistance to go down drastically. Right? But what do you see when you exercise? You see your heart rate go up, and you don't see it, but you don't feel stroke volume, but the amount of blood being pushed out also goes up, so your cardiac output goes up. And this is important, because if this change in cardiac output didn't take place when the total peripheral resistance dropped drastically, your blood pressure would drop substantially. Okay, so there's this teeter-totter effect between the cardiac output and the total peripheral resistance to help maintain that blood pressure within that homeostatic range. Okay. The other factor, blood volume, that's controlled more slowly. These two factors, again, are chiefly regulated by the autonomic nervous system, so we can get rapid effects. Okay. When you start exercising, you need to change that blood pressure rapidly. It would be too slow to change blood volume. Okay. But you can see there's always this teeter-totter effect between those two factors to keep that blood pressure maintained. Okay. And as I said before, Okay, say cardiac output goes up, but total peripheral resistance stays the same. You can see mathematically that would in turn tell arterial pressure would go up. Okay, so if any of these factors increases and the other factors stay the same, okay, cardiac output goes up, blood volume and peripheral resistance stay the same, that means blood pressure will go up. But it's not so nice. There's usually all these counter effects that happen in the body. But any of those factors go up, blood pressure would go up if the other factor does not change. So we've seen that blood pressure is regulated by that cardiac output and that total peripheral resistance. Let's kind of look at how this regulation takes place. Okay, because changes are taking place in the body. If you're exercising, blood pressure is going to be going up. Also, if say you're laying and you stand up, you get a sudden drop in blood pressure. Your body needs to react to counteract this drop in blood pressure. So that first is we need something to sense what the blood pressure is, and that is the function of the baroreceptors. Okay, you have these baroreceptors in the carotid sinus and down here in the aorta. Okay, they are sensing what is the stretch on the vessel walls there. If there's more stretch, that's going to signal those receptors to fire more frequently, and that frequency, that action potentials are sent up to the medulla, where we have these control centers for cardiac, and high frequency would signal, hey, blood pressure is increasing. All right, if there's less stretch, when there's low blood pressure, there's less stretch on those walls, and the firing of these baroreceptors would decrease. And that information would be sent to the medulla. The medulla would interpret that as low blood pressure. So depending on what signal these cardiac centers are getting from the baroreceptors determines what the response is going to be to the region of the heart. Okay, we have parasympathetic, sympathetic that you guys already learned, talking to the SA and AV node, and this would regulate heart rate and in turn regulate cardiac, one factor of cardiac output. So let's do an example. If there is high blood pressure, increased firing of the baroreceptors, a medulla senses high blood pressure. Now it would send out a response through the parasympathetic nervous system. And what do we want? We want the parasympathetic because if we lower the heart rate, that will help lower our blood pressure. Okay, so that is basically that reflex loop using the autonomic nervous system to have effects. All right, but let's look at the full effects. In this example here, we're looking at blood pressure is decreased. Okay, the baroreceptors are sensing a low blood pressure. They would slow their firing rate. That slowed firing rate would be sent to those cardiac centers in the medulla. And the medulla, in this case, because we're talking low blood pressure, we want to activate the sympathetic nervous system. We want to increase cardiac rate. So one factor is increasing cardiac rate. Okay, the other, so this would affect cardiac output, that's CO factor of blood pressure, and if we activate the sympathetic, that's going to cause vasoconstriction. All right, increased vasoconstriction increases total peripheral resistance. Right, so we're getting, actually, remember our blood pressure equals cardiac output times TPR. And you can see the effects that are taking place are we're increasing TPR and we're increasing cardiac output. So therefore we would be increasing blood pressure. And that's good because the stimulus was low blood pressure. Once we get that blood pressure back in homeostatic range, then we negatively feed back to the baroreceptors and shut down this, because we don't want to continually bring cardiac rate up and continually bring vasoconstriction up, because then our blood pressure would climb too high. Okay, so that's kind of the flow of how this works. So now we'll look at how we actually measure this blood pressure and kind of what we would be doing if we were in lab, what we would be doing to measure the blood pressure. So now let's look at how we would actually measure this blood pressure. This is what, when you go to the doctor, this is what they're doing. They're measuring your blood pressure. To do it manually, and this is what we would be doing in lab if we were actually in lab, all of you would be getting connected with a sphygmomanometer. A very mouthful, but essentially that is your blood pressure cuff. Okay, and it's going to go over on your arm where your brachial artery runs. It's the cuff connected to tubing that's connected to the bulb that has a little valve that, when shut off, it's going to allow you to push air into the cuff to inflate it, and then the valve is going to allow us to slowly let out air of the cuff as we go. And you can see as we inflate the cuff, there is a sphygmomanometer that allows you to measure what the pressure is in that cuff. Okay, so what are we doing with this cuff? As you inflate it, you pump it up, right? Before you pump up, your artery is here. Okay. Oh, and one last thing, besides the sphygmomanometer, you also need to have a stethoscope, because what you're going to be looking for is sounds that are taking place in this brachial artery. Okay. But before you pump up the cuff, your artery is wide open. Okay, nothing's pushing down on it. And when the artery is wide open, the blood is flowing basically linear, this laminar flow, nice, and nothing's obstructing it. When there is this laminar flow of blood, there is no sounds being made. Okay, as you start to pump up the cuff, pump, 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 once you exceed diastolic pressure, you're going to start pushing in on the vessel, and as you increase pumping it, you're going to start pinching on the artery. When the pressure exceeds that of diastolic, it's going to start pushing on the artery, right? And when the artery is in this configuration, when it is not completely wide open and not completely shut, there are going to be sounds being made. The blood starts, instead of flowing laminar, starts flowing in this turbulent manner, in this, okay, in kind of all directions. When it's turbulent, that is, you can actually hear sounds being made in the artery from the blood. Okay. As you continue to pump up the pressure cuff, at a certain point above systolic, when you pass systolic blood pressure, you're going to have the artery completely closed, and there's no blood running through, there's no sounds being made. Okay, so completely closed, there's no sounds. Completely open, no sounds. Everything in between, you're going to be able to hear sounds in the stethoscope. Okay, and when your artery is completely closed, it completely closes off just above systolic blood pressure, and when it completely opens is just below diastolic pressure. So you can see we're going to be using these sounds, all right, to figure out where systolic and diastolic pressure are in the artery. Okay. So you pump it up, you get the artery closed off, and then you're going to open that valve slightly, and that allows air out so you can slowly let pressure out of the cuff. And so as you're listening on the stethoscope, you're also watching the pressure, because what you're looking for is to see when the sounds, what we call carotid cough sounds, start. Okay, and those will start when that closed artery starts to open up. All right, and when it would start to open up is when it drops just below systolic pressure. So when we first start hearing carotid cough sounds, that's going to be our mark for systolic pressure. Okay, and here's the carotid cough sounds. Okay, the occluded artery, you can see the blood is turbulent. It's not moving just straight through, linear. Okay. And as we continue to decrease the pressure, when we decrease the pressure, when we're finally just below diastolic pressure, the artery will be wide open again. All right? And what happens when the artery is wide open? We don't hear sounds. So what we're looking for is when we lose the carotid cough sounds, that is what we would pinpoint as our diastolic pressure. Okay, so systolic, you're listening, you're watching the pressure. All right, when you start hearing the thump thump, the tapping sound in the artery, that's your systolic. As you're listening, it actually will get louder midway through, and then when it dies off, you need to be looking at the pressure, and that is your diastolic pressure. Okay. Next slide gives you a kind of... All right, so let's walk this, measuring the blood pressure. Using this chart here, you can see the red here is the pressure. Going up, systolic here, and down is the diastolic. So what we're looking at is when we increase the cuff pressure. So you pump up that cuff. Okay, here's the cuff pressure, is the dotted line coming up. As you increase the right here, you're going to be fully occluding that vessel. It's going to be closed. Okay, when the artery is closed, remember, there is no sound. So you pump the cuff up, you need to make sure you get it above systolic. So we're above systolic here, and now you start letting a little bit of air out. You turn that valve, letting the air out very slowly as you're listening on the stethoscope for the carotid cough sounds. Okay, as the pressure starts to drop, okay, you don't hear anything, but once we reach just below this systolic pressure, the artery is going to start opening and blood's going to flow through, but that blood flow is going to be that turbulent flow. And that turbulent flow makes those carotid cough sounds. So as you're moving through, you're continuing releasing pressure all the way through here, the blood is turbulent. Okay, turbulent, turbulent, turbulent. So you're hearing carotid cough sounds all through this. So what you're listening for is the first sound, and the first sound is going to tell you, hey, that's systolic pressure. And then as you continually release the pressure, just under diastolic, that's when the artery will fully open again. It will look like this. And when the artery is fully open, the blood is now, you can see this is the laminar flow. Just this nice linear flow. There's no turbulence to it. And that is when you will lose the sound. And so as you're listening to the stethoscope and looking at the thing, you lose a sound, you mark that as the diastolic pressure. Okay, and then as you drop it down, the artery is fully open. All right, so first sound, first carotid cough sound is going to be systolic pressure, and then after you lose the sound, that is the diastolic pressure. So the last part, we're going to be looking at what's hemodynamics, or what we're looking at as flow of blood, the forces that involve in circulation of the blood, the flow. All right, and because demands are changing on our body, we also have to change the demand of flow. Sometimes we have to get constant blood flow. When you're exercising, you need to get the flow of blood out to your muscles very quickly so you can supply those muscles so they got enough nutrients and oxygen to keep them forming. When you're resting, you're going to shut blood flow to your organs, but you don't have to have this high demand. It doesn't have to, you're at rest, you don't have to have this. So with these changes that are taking place, okay, we have to change the flow of blood. So let's look at what controls this. You can see exercising. Here's your body at rest, and you can look at the flow of blood to the different organs. Then, when you go to exercise, you can see there's a greater flow of blood, and there's going to be a large flow of blood to the muscles. Okay, in eating, blood flow, you tend to shunt more blood to the digestive tract. So let's see how we're able to regulate this flow to these different organs. Right. So some factors in your autonomic nervous system is going to be in play here, since we're talking cardiac and we're talking blood vessels. Those are all smooth muscle or cardiac muscles in control of under the control of the autonomic nervous system. Right? One factor in hemodynamics is the cardiac output has an effect. If you're able to push more blood, that's going to cause more pressure and cause more flow. Our sympathetic, you can see what's its effect. So the sympathetic, you can see here, innervates both the SA and AV nodes, but the sympathetic also innervates the cardiac muscle. Okay, and so it has two effects on cardiac output. It increases heart rate, but because it innervates the muscles here, it also increases the force of contraction, what we call contractility of those heart muscles. Those heart muscles can contract kind of weakly, or they can contract very forcefully. And if you contract very forcefully, you're going to increase stroke volume. So the sympathetic increases stroke volume and heart rate. Those are the two factors that determine cardiac output. Right, we will see the sympathetic also will help regulate blood flow by altering blood vessel diameter. Okay, so diameter of the blood vessel, we can have dilated, wide open, or constricted. Right, dilated or constricted. So the sympathetic innervates the muscles of those, the arterioles, the muscle walls, and if it causes contraction, that's going to cause constriction. It will make the vessel diameter smaller. Okay, that's going to limit the flow of blood. Whereas if I have a nice big open diameter, that's going to allow more blood flow. Okay. On the other end, the parasympathetic. The parasympathetic, you can see its only input in regulating this is heart rate. It lowers heart rate. Okay. So the sympathetic is going to increase, parasympathetic is going to lower the heart rate. We're going to see. So Poussier's law. This gives us all the factors in blood flow rate. Okay. What is the rate of blood flow? And it's equal to pi, that's a constant, times the change in pressure. So since we're looking at blood flow through a vessel, right, the change in pressure has to do with, okay, what is the pressure at the beginning of the vessel and pressure at the end. And we'll say P1 and P2. Okay, so if I subtract P1 minus P2, that would be my delta P. Okay, if this is larger, if there's large pressure here compared to the end, that's going to allow blood to flow more quickly. And you can see the delta P is in the numerator of this equation. So as delta P increases, blood flow increases. Okay. The other factor in the numerator is R. R is radius of the vessel. So diameter's 2 radius. So if the vessel is dilated, R is going to be greater. If R is the blood vessel is constricted, then R is a smaller value. What you can see here mathematically is what is going to have the greatest effect on blood flow. The radius is to the 4th power. Okay, so let's just do, say we doubled the delta P, came 2 times larger. It originally was 1 and now it's just 2. That would cause blood flow to be twice as fast. The rate of flow to be twice. But what if we made the radius 2 times larger? We went from constricted to dilated and we made the radius 2 times larger. Now we got 2 to the 4th power, which would equal 16. So blood flow would be 16 times greater with a doubling of the radius. So you can see the blood vessel diameter is going to be the biggest way in which we regulate the flow of blood. Okay, again, that's controlled by sympathetic nervous system, and also we'll see circulating levels of epinephrine. Okay, the other 2 factors in the denominator here are blood viscosity, so how thick the blood is. And you can see if the blood becomes more thick, the N is in the denominator, that will make blood flow slower. And then blood vessel length, which doesn't change greatly, so L's not going to be of great factor. It doesn't change real drastically. The thing we can change very quickly is these up here. Okay, but you can see there's some disorders if you had lots more blood cells in the blood, or if you were highly dehydrated, that would affect, you lose water, that would affect the viscosity. So there are some effects on here, and if N or L go up, since these are in the denominator, then blood flow would decrease. Okay, so those are the factors. You're going to be looking at lab at these different factors in blood flow, but one thing to really make point of is what is going to have the largest effect on blood flow, and that's going to be the radius of the blood vessel, okay, whether dilated or constricted. All right, well, here's the difference between, this is the R, changing R, here is dilation of the artery. Here's where your artery normally is at rest. It has a little bit of constriction, so it's not fully dilated, right? That's going to limit some of the flow, but vasoconstricted, when the arterial walls are constricted. Okay, when these muscles, smooth muscles around the walls contract, that's going to decrease the radius and therefore decrease the blood flow. Okay, so sympathetic, you see hormones, epinephrine, Okay, that's the big factor when you start exercising. Okay, you want to have massive vasodilation to your skeletal muscles, and kind of the main player in vasodilating to the skeletal muscle is going to be you release epinephrine in the blood, and that's going to cause vasodilation, and that's going to open up the vessels to the muscles, and you're going to get more blood to the muscles so you can fuel that exercise.